Thank you very much, Massimo, for having come. Massimo Stella is a researcher on complex network problems, and he is also the founder of a company that studies some practical issues, I think, on these problems. So I give the floor to Dr. Massimo Stella. Please, Massimo.
Thank you. Thank you so much for inviting me, for having me. Today, my lecture will be about multiplex lexical networks as models of language representation in the human mind. And I think that this is a very exciting topic. I'm really happy about also being part of this workshop. My work at Complex Science Consulting is about developing new models of language representations for informing mainly research projects, but also private industries about the ways that and the mechanisms behind language processing and cognition. And I think this is an exciting topic because it's at the same time old and new. It's old because it relies on decades of research in psychology and cognitive sciences about models behind the processing of language and the mental representation that we build in our minds of language. But it's also new. It's new because it uses the new tools from machine learning, artificial intelligence, data science, and complex systems in order to assess and test the quality of those models from cognitive science and psychology. And this is really, really fascinating. There is very many things to do, as I would like to point out in this presentation. This presentation will mostly be structured in 3 different parts. I would like to start with a simple introduction of complex networks, and I would like to talk a bit about this fascinating definition of the mental lexicon. Then I would like to briefly introduce some technical measures and some definitions about multi-layer and multiplex networks. And then the last part, which will be the longest one, will be about my research with multiplex lexical networks in cognitive science, about mostly 2 different patterns: the investigation of a core in the mental lexicon and its relevance for assessing creativity levels in people and for studying language processing in people with aphasia, with clinical conditions. And the second pattern will also talk about using multiplex networks for predicting early word acquisition. And I would like to start with this fascinating idea of the mental lexicon, which in itself is just an idea, a model. The idea is that there is this cognitive system that we really don't know much about. We don't even know whether it is really one system or several systems that interact together. What we do know is that the circuits of the brain give rise to a set of cognitive mechanisms that in turn are responsible for acquiring, storing, processing linguistic information. Words together with their content. So the way we write words, the way we pronounce words, the meaning of words, and also similarities between words and concepts. Historically speaking, this concept of the mental lexicon started with the metaphor of the lexicon being a sort of dictionary in the human mind. Although unfortunately this is not really the case, we will see that there are several differences. But before I turn to highlighting the similarities and the differences, I would like to suggest these 2 books here, one by Professor Jan Hutchinson and another one by Professor Michael Vidovich. Both of these books contain decades of psycholinguistic research telling us that the structure of this mental lexicon is quite important for influencing a lot of different phenomena related to the way that we acquire and use language. coming back to the dictionary metaphor, if we think of the mental lexicon as a dictionary, the first thing that we need to keep into account is that the dictionary works basically at the level of individual words. So the information in this case focuses mostly on specific words. And we already know that in the mental lexicon, this is not really the case. Words in our mind, they are made of phonemes, of simpler units, but also we can think of words in combination with other words in sentences. And these combinations can drastically alter the meaning that we attribute to words or the way that we perceive these words. So this is already a strong difference. The mental lexicon is not just a dictionary as a list of words. It's way more complex than that. And another difference is that the mental lexicon contains associations, conceptual associations between concepts. However, this difference is not that strong because if one considers also the definitions in a dictionary, like defining what water is, well, even from these definitions, we might find a way, and we will see also in the following, we might find a way to build conceptual associations, semantic associations between different words. What's interesting is that in the mental lexicon, several types of conceptual associations, several types of conceptual associations can coexist together. Like, for instance, two words might overlap in their meanings and be synonyms, or one word might be the generalization of another one, or a specific type of another one. And these are semantic associations, but there might be also other types of associations, like, for instance, phonological similarities, the fact that two words differ by the addition, division, or substitution of one phoneme, and thus sound similar, like cat and car. And also, there might be memory recall patterns, like free associations. Reading a certain cue word makes one think of another word. These different types of associations coexist together in the mental lexicon and are somewhat present in there, like decades of studies about semantic and phonological priming have shown us. However, this leads naturally to a distinction between the dictionary metaphor, like the dictionary and the mental lexicon, whereas the dictionary considers just a list of words in isolations. The mental lexicon considers words organized in a much more dynamical structure, where these kinds of associations are really present and they drive the way that we process words. We will be seeing this in the next stages. So what I would really like to underline is that if we want to investigate the mental lexicon, we cannot stop at the idea of considering just a list of words. We need to consider the structure of conceptual associations between words. Accessing this type of representation can be extremely powerful in the inquiries that we want to do about understanding how cognition drives language processing. Okay, so we were talking about differences between a dictionary, a static dictionary structure, and a more dynamical structure of a mental lexicon where conceptual associations are really present and they are of different types and they coexist together. Historically, however, the idea of considering conceptual associations as a structure of the mental lexicon focused only on one type of conceptual associations. And this is the work by Quillian, dated 1967, that in the abstract writes, in order to discover design principles for a large memory that can enable it to serve as a base of knowledge underlying human-like language behavior, experiments with a model memory are performed. This model is built within a computer by recoding a body of information from an ordinary dictionary into a complex network of elements of associations, interconnected them. And this is really a groundbreaking paper. The idea here is that, yeah, words in a mind have a certain structure that we can sort of extract from a dictionary, but this structure has a network structure. And once we build this network structure, we can start exploring this representation of the mental lexicon, and we can start using this network for doing something. The plot that I'm reporting here considers words as nodes, like canary, bird, and animal. And these concepts are connected in a hierarchical way, depending on the specific semantic features that they have as obtained from a dictionary structure. But what is this network structure useful for? What can it be used for? Well, in a subsequent paper, Collins and Quillian used this hierarchical network structure in order to investigate cognitive data about judgment rates. So they had a certain number of participants, and these participants were given simple statements like a canary can sing. The participants had to read the statement and judge whether the statement was true or false as quickly as possible. And the cognitive data in this case was measuring the time that it took for people to judge whether a sentence was true or false. What Quillians and Loftus observed was that for sentences merging together two concepts that were farther apart at a higher network distance on this hierarchical network structure, well, concepts that were at further network distance corresponded to longer times for identifying whether that sentence was true or false. And Collins and Quillian concluding from this that semantic distance on this hierarchical network structure was a predictor for the time that it took for people to navigate through conceptual associations and process the language of a certain sentence. So that it is extremely important to consider their approach because their paper was the first one that used network data, a network representation of the mental lexicon, in combination with cognitive data in order to assess whether there was some sort of cognitive processing and make also predictions out of it. Unfortunately, now we know that most of these things have limitations. And also don't do the mistake of considering that really the mental lexicon is just a hierarchical network. This is only one way of representing concepts in the human mind. The difficulty with the mental lexicon is that we really don't know how it is structured, and we cannot really bring it to the lab and dissect it and access it like we could do with the human brain. With the human brain, we might slice it up, we might reproduce it in the lab, we might bring few more, we could directly access to the system. With the mental lexicon, since that's an idealized system, we cannot do so. What we can access in the lab is a representation of the mental lexicon, which in this case might be a network. However, that network has some features or some limitations. Like in this case, the hierarchical network structure considers that each node has a set of features that need to be replicated in order for the hierarchy to be built. And this is already something quite difficult, quite memory consuming. Also, unfortunately, the network distance that Collins and Quillian used does not take into account how general concepts are. And we do know from psycholinguistics that concept generality is an important feature for predicting the time it takes to process concepts. Also, the cognitive data that they gathered displayed some problems because there were some statements that were close to being real but implausible, and for those statements there was no growth according to the network distance. So they also had issues. This paper was highly criticized in the literature, so that in a subsequent paper by Collins and Loftus, they tried to rearrange this idea of a strict hierarchy of concepts and make it look like a complex network that is still based on semantic features, but now has the advantage that concepts can both be close together, semantically closely related with each other, and this is indicated by shorter links, but concepts can also be loosely semantically related, and be indicated with longer links. So what Collins and Loftus did in the 1975 paper was transitioning from a strict hierarchical structure of the mental lexicon to a complex network-like. That was the first paper that officially talked about the mental lexicon in terms of concepts. It didn't do any sort of specific implementation of this complex network, but it provided a few ingredients. The idea was that concepts were represented as nodes. They were connected together according to the amount of semantic features that they shared. Like, for instance, is it a color? Is it alive? Is it visible? These can be encoded in 0 and 1s for concepts possessing or not possessing a certain feature, and then a certain similarity matrix can link such concepts. This would also automatically lead to some links being stronger than others, according to the amount of semantic relationships, semantic features shared by concepts. There were problems also with this recipe for investigating the mental lexicon. The first one, what are the semantic features that make concepts link to each other? The definition of this set of features is definitely non-trivial, also because it requires extensive data about the different features that we want to consider. And this is something that at that time, in 1975, this was not feasible. Also, in terms of modeling conceptual relatedness, we need to consider a specific function that enables this. And it's extremely difficult to do it without a cognitive indication. Also, this model could not account for negations and implausible clauses. So it was particularly difficult for these kinds of linguistic processing. So also the paper by Collins and Loftus was actually neglected. Other ways for considering conceptual associations between concepts based on machine learning and neural networks were rather preferred in the literature. So this paper was sort of abandoned. This idea of complex networks giving structure to the mental lexicon was also strongly resisted in the field, in the area of psychology. However, very interestingly, already in the 70s, the paper by Collins and Loftus talked about multiplex networks, because they state in their paper that there is a semantic aspect of the mental lexicon where semantic features make semantic connections between concepts, but there is also a lexical, a phonological one, where concepts are linked together if they share, if they differ by the addition, substitution, or deletion of one phoneme only. So this is already quite interesting, because they already thought of two types of networks, a semantic and a phonological one, being connected with each other. Unfortunately, they only wrote about it. They didn't do any numerical simulations or any investigation. And the paper was also forgotten in the scientific literature, so that in the end, the idea of multiplex lexical networks was lost. What wasn't lost was the advent, this idea of giving structure to the mental lexicon through complex network representations. This idea persisted in the literature. It was also revived thanks to the advent of network science in the physics community. And I would encourage for you to check this very nice literature review by Professors Castro and Hsu about the contributions that modern network science gave to the cognitive sciences. This is a really fascinating story. Nowadays, psycholinguistics and cognitive sciences are rediscovering complex networks as powerful tools for modeling the mental lexicon and for predicting and understanding cognitive data. So the contribution of Collins and Loftus has been reevaluated. And the idea is that since the mental lexicon can influence a wide variety of processes and phenomena, maybe the problem is not really considering only one type of complex networks. The key challenge must be considering multiple types of networks, that each one codes for a certain type of process. But then this automatically leads to another challenge. How do we link together these kinds of networks? They might model different phenomena, but how do we connect them together and treat them together within the same formalism? And a possible answer to this question, there can be many, but a possible answer can be multi-layer networks. Now, in the second part of the talk, I would like to give just a few mathematical definitions for understanding how multi-layer networks and multiplex networks differ from usual single-layer complex networks. We all know that informally, a complex network is just a graph that represents interconnections between entities. These entities are called nodes, and they might represent very different things. In the mental lexicon, they might represent words or phonemes, and so on. Links can be represented mathematically by an adjacency matrix whose entries, A, I, J, the general entry, is either 0 or 1. It's 0 if nodes I and J are disconnected in the network. It's 1 if nodes I and J are connected. For instance, in this network, we have nodes 1 and 2 that are connected, so the entry A1, 2 will be a 1. All networks that can be represented by one matrix are called single-layer networks. The networks for which this is not possible, they can still be treated as a collection of different adjacency matrices. Multi-layer networks are exactly collections of different layers of networks. Each layer has its own set of nodes and its own adjacency matrix. The whole network can be represented by a super adjacency matrix. Let's see a brief example. We have here a two-layer multi-layer network. This layer alpha contains 3 nodes and these connections that are encoded in this adjacency matrix. The layer beta contains 2 nodes and connections that are encoded in this other adjacency matrix. So we can build a super adjacency matrix that contains on the main diagonal the adjacency matrices of the individual network layers. What's off the diagonal, of the blocks? There are 2 other matrices that encode connections between nodes from different layers. We call these connections interlayer links, whereas instead connections that stay within the same layer are called intralayer links. Now, this is really the key component of multi-layer networks. The fact that there can be both interlayer and intralayer links makes it possible for random walkers or for cycles to appear between nodes that combine 2 or more layers. Like in this case, for instance, we might start at node 1, then stay in layer alpha and go to 2, then jump from layer alpha to layer beta, go to 5, then from 5 to 4, and then from 4 back to 1. So that the addition of these multi-layer links make it possible to create a cycle that goes from 1 to 2 to 5 to 4. So this and then back to 1. So this creates new ways of navigating the network. And this is very much similar to what we do in transportation systems. In transportation systems, we have different layers of connections between places, and the availability of all these layers make it possible for us to start in one node, then transition to another type of transportation, go to another part of the network, then transition again and get to another part. So that the possibility of making jumps across layers facilitates or drastically alters connectivity and connectedness between different nodes of the network. These jumps will be extremely important in the following. Another feature of multi-layer networks is that they can have this so-called alignment. And this is what differentiates between multi-layer networks in general and multiplex networks. These 2 words, multiplex and multi-layer, they are not synonym. Multiplex networks are specific examples of multi-layer networks. And the difference is that in a multiplex network, the same set of nodes needs to be replicated across all the layers, so that it's possible to identify one node and then all its replicas across all the layers. This feature is called full alignment. And this is not always the case, because in some multi-layer networks, it might be that one node is existing on one layer, but it doesn't exist in another one. This full alignment makes it possible to consider all the replicas of a certain node, and all these replicas become a so-called physical node. Let's get back to the mental lexicon. In a multiplex representation of the mental lexicon, the physical node might be the word in its entirety. However, in synergy with the psychological theories about the mental representations of concepts in the human mind, we might think of the semantic aspect of a given word as being a replica node on a layer of semantic similarities, and this semantic aspect would be the lemma of a certain concept. However, we know there should be also a phonological representation of this word, the so-called lexeme, and this would be a phonological aspect of the word, which might be a replica node of the same word on a layer of phonological similarities. So the idea is that in multiplex networks, multiplex lexical networks, nodes represent concepts, but these concepts can have both semantic aspects, lemmas, and phonological aspects, lexemes. So this is already something that we get into account. And in this way, if we do this alignment across layers, we can also connect words differently. On one layer according to semantic similarities, and on another layer according to phonological similarities. So this is a way of accounting for both semantic and phonological similarities, like Collins and Loftus wrote in their original paper. These two representations are actually the same. So in here, I just differentiated the two layers. In here, I collapsed everything onto one layer, but I kept links with different colors. This representation is a multiplex network, but it's also called edge-colored graph. Now, the real question here, okay, we can build a multiplex of like 1,000 layers. What's the matter? Why does it work? Why is it important? Or is it really useful? It might not be useful, because accounting for so many layers might actually include redundant information. Why don't we rather compress all the layers into a single layer network? In the end, if we do this, we lose some information about the connectivity of the original system. Let's consider this very brief example. We have a multiplex network here, and we know here that some nodes, for instance, are disconnected in one layer. But if we aggregate all these layers together, like in here, these nodes, they don't appear disconnected anymore, they appear connected. So we are losing some information about these nodes. Also, if we consider cycles, like previously, if we consider jumps, we can go from this node to this other one, and then to this other one, to this other one, and then jump, and then to this other one back. So there is a cycle here, and this cycle is mostly belonging to this layer, and then a little bit also on this other layer. And if we aggregate this together, we lose this information. We just get a cycle that it's here. It's like this. So whenever we aggregate layers together, we lose some information about the original system. The question about adding more layers against the question of like compressing all of them can be solved by searching for the optimal number of layers that reduce the information loss, while also guaranteing that redundant information is just aggregated together so that it doesn't occupy much space. It's like using a zip compressor when we want to compress files. We want to do a similar feature here. We don't want to build representations of the mental lexicon that consider redundant information, but we also want to consider diff aspects of the mental lexicon that encode more information than the aggregate. And we can do this in different ways. There are different approaches. I reported here a very recent methodology, but I also used other ones in my papers that guarantee that the information that we are considering, the different aspects of the mental lexicon that we are considering, are really separate. They are not the same thing called with different names. They are not redundant information. Another important thing to consider, and then we will get to the juicy parts of the research component of this talk, is that multiplexity changes the connectedness of words. In single-layer networks, nodes are connected if they have at least one path between them. In this network, in case there is only one layer, these two nodes are connected because there is a path between them, a link, and this node is disconnected. In multiplex networks, connectedness might be roughly the same. However, the path can use links of any color. There is no restriction. So in this multiplex network with two layers, with two colors, these three nodes, they are connected because there is a path that goes through all of them that combines, in this case, different colors. In here, let's see if I move you here. In here, these three nodes, they have a different layout. And in multiplex networks, there is also another definition that is mutual connectedness or viability. Viability is the requirement that nodes must be connected across all single layers in the sense of single layer networks. So this means that if I consider only blue links, then these nodes must be connected by using only blue links, and they also must be connected by using only red links if they have to be viably connected or mutually connected. So in a multiplex lexical network, mutual connectedness is a much stricter requirement than normal connectedness. And we can talk of two different connected components. One is the largest connected component, which is just the component of all connected nodes. For instance, in here in this representation, this node is disconnected, but I can jump to another layer, and in here this node is connected and it goes to other nodes, and then I can go back. All these nodes are connected with each other because there are paths of different colors. However, if I consider the viable component, the mutual connectedness, only these three nodes here, they have a path that connects them on both the layers at the same time. Viability is a more restrictive definition of connectedness, and it arises in multiplex networks. So this is a feature of multiplexity. My question is, okay, what about how does it translate? So viability, what does it become in single layer networks? When I have only one color available, viability automatically becomes connectedness for single layer networks. On multiplex networks in general, the viable component is a subset of the connected component. Okay, and now all these mildly obscure and boring mathematical terms are over. We get back to the research part, the research component. We will answer a set of research questions. The first one is, if we consider a multiplex representation of the mental lexicon, is there a core in this representation? What we did in a scientific report study in 2018 was considering 8,500 English words connected across 4 different layers, considering free associations, words that remind each other in a memory recall task, synonyms, words sharing their content, their meaning in a certain context, taxonomic relations, one word being the generalization or a specific type of another word, and also phonological similarities, which will be discussed more by Professor Siu in her talk later, tomorrow, I guess. Phonological similarities are just based on the idea that two words can differ by the addition, substitution, or deletion of one phoneme, and they might sound similar. The combination of these four aspects of the mental lexicon, with three different semantic aspects and one phonological aspect, led to a multiplex lexical network. This was obtained by merging together a variety of different datasets, including also the age of acquisition of words, the average age at which a certain word was acquired by a certain population of English native speakers. We use these data in order to model the growth over time of the mental lexicon. But before we did that, we tested whether or not this representation, this multiplex representation of the mental lexicon, contained redundant information, so that we had to collapse together, to aggregate together any two layers. We applied an information theoretic methodology that highlighted that the configuration of layers containing the most information compared to the aggregate was the configuration in which all the four layers were kept as separate. So that this is a quantitative information that the connectivity, the cycles, the disconnectedness, the connectedness of all these four layers is different enough that they should be kept as separate. So they should be considered really as separate aspects of the mental lexicon. And this structure can thus be used for further cognitive requirements, for cognitive validation now. The idea was investigating the growth over time of the mental lexicon. Consider one word is added according to the age it is at which it is acquired, the mental lexicon growth, and we studied the viable component of the mental lexicon. So these clusters of nodes being connected across all layers at the same time. And we did it for normative acquisition of words, so acquiring words according to the age at which they were acquired, over a time window of 15 years. And we also did this growth according to the frequency of words, so acquiring first higher frequency words and then less and less frequent words. And we also did it for random acquisition, averaging over a few thousand simulations where words were acquired at random. We plotted the size of the largest viable component over age. And we noticed that around age 7 and 8, there was an explosive phase transition. And I think that this picture conveys quite well the idea of the explosiveness, but it's not really an explosion. The network is really not exploding. It's just that there is a sudden jump in the size of the viable component, so that in the beginning there is nothing. Adding only one word makes the viable component appear and possess already a few hundred words in it. And then the viable component, the more words that are included in the mental lexicon, the larger this viable component becomes. This transition, this explosive phase transition, is a phenomenon well studied in multiplex networks, and this is a sudden change. Corresponds to a sudden change in the connectivity of words in the multiplex network. This sudden change is not reproduced by a frequency effect that leads to two changes at later ages, and it's also completely invisible to random acquisition. In this case, there is a continuous phase transition in the emergence of the LVC. So the fact that these two null models do not reproduce this sudden change is already a hint that this change might be important for cognitive development. And also this change appears in a time window that is particularly critical for the development, for the cognitive development of children. And also it is in an age where we know that some lexical restructuring takes place. So the reorganization of phonological forms in combination with their meanings. And we also know that in this age, there is a critical development of writing skills in young children. So this is a critical age where sudden cognitive development appears, and we have an indicator that the connectivity of words in the mental lexicon of children is also undergoing a very critical transition. Unfortunately, we don't have enough power in order to say that really like this LVC is really a sign for improved cognitive processing. But we can do a little bit better and trying to understand whether this sudden change, this explosive change, might also be reproduced in connectedness or in other components that are not multiplex, like the connected component. And in all the plots here, let me bring you here on this side, we notice that in the aggregate network, you remember if we consider the aggregate, then the viable component becomes the connected component. Well, we see that the connected component of the multiplex network doesn't undergo any kind of explosive phase transition. The same also for all the other connected components. So we have a phenomenon that is present in a critical time window, and that is present only if we consider multiplexity. This phenomenon is invisible if we consider single layer networks. We cannot say much about the cognitive importance of this core yet, but we can say more about the network characterization of this viable component. And we can do this by considering the network definition of cores. In network science, a network core is a set of tightly interconnected nodes, so that the probability that a link occurs between nodes inside of this core is higher than the probability of links occurring between nodes in the core and outside. And this probability itself is higher than the probability of any link connecting any two nodes outside of the core. If we observe this range of inequalities, this sequence of inequalities, we can identify a network core. And we did this in our multiplex representation, and we found out that yes, the LVC respects this definition of network cores across all layers, so that the viable component is really a network core of the mental lexicon. This is an interesting perspective here. This is a network core, a part of tightly interconnected concepts that persists across different aspects of the mental lexicon. What's also more interesting from a psycholinguistic perspective is that this core is made of words that are somewhat special. Words inside of the LVC are, in general, richer in terms of different numbers of meanings. They have more meanings. They have a higher frequency. They are recognized in lexical identification tasks quicker than words outside of the LVC. Words within the LVC are also more concrete. They are acquired earlier, and they tend to be shorter also. All these features, have been studied in the literature separately, and they've shown to bring an advantage in processing words. Words that are acquired earlier, they are shorter, they are more concrete, they have more meanings, they have a higher frequency, they tend to be processed with less efforts in a variety of different lexical identification tasks, picture naming tasks, in a variety of cognitive tasks. The fact that this viable component is very rich in terms of these special words, means that this viable component is also somewhat special in terms of psycholinguistic norms. And the effect of this viable component on the overall system is that it makes it makes concepts way closer together. We tried removing progressively this LVC from the multiplex network, and we tested what happened when we removed these nodes. We tested what happened to the average network distance between any two remaining concepts. We know from other studies, and you will probably see this with the lecture by Professor Kenneth this afternoon, conceptual network distance is an important predictor of semantic relatedness and also phonological relatedness. We don't know whether it always has a positive effect, but from the recent evidence that we have right now, we do know that concepts that are closer together might take less time to be processed together in semantic priming experiments and in other types of experiments. So in some instances, closer network distance means facilitation of word processing. This is not always the case. There can be also other types of interference. But we do know that network distance is important. It has an influence over the way we process words. If we get rid of the LVC, if we get rid of words outside of the LVC, nothing happens to the average distance of words in the mental lexicon, as if nothing happened. We can remove up to 1,200 nodes, 1,200 words, and nothing happens to the average distance between words. When we remove these 1,200 words from within the LVC, however, we notice that the closeness, the average closeness between words decreases a lot. And concepts become less and less close with each other if we remove words within the LVC. An objection might be, okay, yeah, but words in this viable cluster have a higher degree than words outside, so what you're seeing is just an effect of taking out hubs from the complex network. We tried removing also nodes from outside of the LVC, but with the same degree in the LVC. And we still notice that removing nodes from the LVC with the same degree led to a stronger decrease in closeness. So these removal experiments indicate that the LVC is a network core that is making concepts in the mental lexicon close together. So this core is fundamental in providing shortcuts that facilitate a navigation in terms of shorter network distances between concepts. We don't know yet if this shorter network distance always facilitates conceptual processing, or it's rather facilitative in some instances and inhibitory in some other instances. But we do know that this viable cluster influences the semantic and phonological distances between concepts in the mental lexicon. So this is already a very interesting result. There is a core in the mental representation of language. This core becomes visible if we consider multiplex networks. It is invisible otherwise. And we do know that this core is rich in special words and it makes everything well connected. But what does it mean for language processing? This is, I guess, what many of us are wondering, and I'm wondering as well. There is so much research to do here. With a collaboration with Professor Kennett in 2019, we used some data that he gathered for another paper about creativity levels in people. We had a population of 94 individuals that were categorized in two classes, people with high creativity levels and people with low creativity levels, according to two scores coming from a fluid intelligence task and from the self-assessment creative achievement questionnaire. These participants, these people, were asked to engage in an animal fluency task. It's a very nice task, very well studied in the literature in psycholinguistics, but it's also very simple. The task is name as many animals as you can in 2 minutes. And the outcome, the result, is just a sequence of animals: dog, cat, bird, like the list here. What we did was using a multiplex lexical representation of words in order to detect features of these lists of animals produced by participants with a high level of creativity and with a low level of creativity. And we checked the positions of these words within and outside of the LVC in this mental lexicon structure and studied a certain number of different features. I don't have time to go through all of them, but I encourage for you to check the original paper. We found interesting differences in the ways that people with high creativity and low creativity levels produced words over this mental lexical structure. So imagine that there are different strategies, different mental search processes that drive retrieval of animal words across a certain multiplex network. We don't really know how it works, but we can check the outcome. And okay, we notice that yes, people with a high creativity level in general produce more responses than people with low creativity levels, but this was well expected. This is also has been found in other studies. What we found was that people with low creativity levels, they tended to produce more responses that fell into the LVC, into the viable cluster. They also tended to cover less nodes when visiting concepts from one concept, from one animal to another one. They did a shortest, we assume that they did a shortest path. Well, the shortest paths made by people with a higher creativity were longer than the shortest paths taken by people with a lower creativity level. Also, these kinds of shortest paths from the general category of animal, they contain more accesses to the LVC in people with low creativity levels. And also, people with low creativity levels, they tended to get inside and outside of the LVC much more frequently with a higher entropy compared to what people with a higher creativity did. So in general, participants with a higher creativity level produced more responses outside of the LVC. They could navigate longer distances, and they did less accesses to the LVC than what people with a lower creativity level did. This is an indication, these differences indicate that people with lower creativity levels recalled animals by accessing more the viable cluster. And this indicates that the viable cluster plays an important role for supporting lexical retrieval in absence of other strategies that we know have to be present in people with a higher level of creativity, like different ways of searching for concepts or different fluid intelligence strategies of navigating the mental lexicon. We do know that people with high creativity are very good at connecting together concepts that are far apart on network distances. And this is also what we found with our paper. So we found that the LVC facilitates lexical retrieval or supports lexical retrieval that is a sort of basic level in people with low creativity level. The LVC is not really accessed that much in people that can navigate more and more in the mental lexicon, in more peripheral areas of the mental lexicon. This difference was also interesting because we used it for implementing an automatic assessment of creativity levels. A very simple one. Imagine that you produce just a list of words here. You do the animal category task. There is some processing of this list of words according to the data coming from a multiplex lexical network. And then there is a very simple machine learning classifier, a logistic regressor, nothing really fancy, that together with the splitting of training and validation sets and cross-validation, enables an automatic prediction of creativity levels. It can tell if a person has a high or a low creativity level just by considering a few words produced in 2 minutes of a task. And the accuracy of this classification is not stellar. It's rather around 65%, which is not good enough for clinical applications. In clinical applications, at least an accuracy of 75% should be achieved. But this accuracy is way higher than random expectation in the balanced case where you have the same number of people with a high and low creativity levels. The expectancy would be 50%. So this is way higher. And let me stress that this model works with very few features that come from a network perspective and from a few psycholinguistic variables. So this is a very simple model that already is capable of detecting differences in the way people with a high creativity and low creativity access the viable cluster, this core of the mental lexicon. Further research, future research is required in order to improve these results by adding more and more features or by changing the modeling approach in order to assess the creativity of people with automatic approaches. And there is a very active, prolific research field nowadays in quantitative data science in using different types of machine learning and complex networks for predicting the creativity of individuals. What I would like to stress is that we tried to investigate also the importance of the LVC in clinical populations. I did this through network attacks and also by collaborating with other experts from clinical sciences in order to predict the production of words in clinical populations in people having aphasia. What I did in this paper was considering a lexical representation of the mental lexicon, including 16,000 words, organized across two layers. A layer of free associations coming from the small world of words, a very interesting project led by Simon Didin, and gathering free association data for 12,000 English cues. There are many English words that are present in this data set, and they just encapsulate free associations. So reading a certain word, what does it elicit in the mind? What does it make it think of? This was one layer. The other one was a layer of phonological similarities, and it was based on, again, similarities of sounds. In this structure of 16,000 words, I simulated random network attacks. A network attack is the idea that one node, when it's attacked, it becomes unavailable for connecting together nodes. For instance, if we attacked this node here, we would lose also all its connections, and this system will become disconnected on this layer. The idea of attacking networks is quite common in network science, and it can bring results for understanding how the connectedness is actually organized in specific systems. There are many ways with which we can attack nodes. We might attack, for instance, first the nodes that have a higher frequency, or nodes that have a high degree, or nodes that are in the middle of the network somehow, that have a high page rank. We could also attack nodes according to aphasia-style attacks. What are these kinds of attacks? In this paper, I used the clinical data coming from the Philadelphia naming task and curated by the MRRI. This data is basically a picture naming experiment where people are shown a picture and they are asked to produce the name of the drawing reproduced in this picture. The people that perform this picture naming task are control people, healthy people, but also people with clinical impairments like aphasia. Aphasia is a clinical condition where language is impaired. It is mostly related to injuries of the brain, but there are different types and different severities of the disease, so that people can just find some difficulties in finding words and producing them, or their language understanding might be disrupted, or their language production might be disrupted. There are different scales. The most basic one is anomic aphasia, where people have difficulties in finding the correct names for naming things. In this dataset, there were 31,800 other utterances of people with anomic aphasia trying to name a set of 173 words that were present also in my multiplex lexical network. And what I did was estimating with a logistic regressor the probability for correctly pronouncing a certain word by using as predictors a certain number of different word features, both from psycholinguistic norms like frequency, length, age of acquisition, number of meanings, and so on, and also from the network representation. I would like to stress that this type of prediction is quite insightful and quite powerful in predicting the correct probability of people pronouncing words, but also in terms of predicting the types of mistakes that people with aphasia can do. They can make semantic mistakes. They can name a certain object, but they wanted to produce another one that comes from another semantic sphere. They also might produce a name that sounds like another one and thus do a formal error. We investigated these types of mistakes in a recent paper with Professors Castro and Siu. What I did here instead, in this network attacks, was using this probability for ranking nodes and perform some degradation of the mental lexicon that mimics the way that language is degraded in people with anomic aphasia. And then I performed these attacks and I checked how the cognitive component and the viable component of the multiplex network degraded after a certain number of nodes were attacked and removed from the network. And I found that the cognitive component is in general robust to most network attacks because it decays in a linear way. And this linear way, so linearly proportional to the number of removed words. And this way of degrading in network sense is called gracious decay. So the mental lexicon is robust to most attacks based on removing first words with a shorter length, removing first words with a higher frequency, words acquired first, and so on. However, the mental lexicon is also fragile to attacks based on multiplex degree. In fact, if we remove words that have a high total degree between semantic associates plus phonological associates, well, we notice that there is a first order phase transition. This is a critical phase transition. It's called also catastrophe in dynamical systems. It's basically related to the idea that by removing a very limited amount of words, we can actually disrupt the whole system and change it. You remember that in the whole multiplex network there were 60,000 words. If we remove only 1/3, but based on this multiplex degree, we can actually disrupt connectedness completely among the remaining 10,000 words. So this is quite a catastrophic event. And this also calls for the necessity of using multiplex degree rather than just semantic degree or phonological degree separated in future studies about cognitive processing and language processing. Hubs in this mental lexicon are extremely important for connecting words together and should be studied more in the future. What happens to the viable component? If we remove first words that have a high probability of being correctly named by people with anomic aphasia, we're able to dismantle completely the viable component by removing roughly 900 words. So this indicates that the logistic inference performed on such a small number of words, and this is a limit caused by the availability of data, well, even doing this inference on a small amount of words is capturing central words whose removal destroys the viable component roughly as much as other types of network attacks can do. And the attack that dismantles very quickly the viable component is attacking words with a high multiplex page rank. Page rank on multiplex networks is essential for connecting again nodes with each other and letting the flow and guaranteeing the flow of random walkers across a network structure. So these two results tell us that the viable cluster is again important for connecting nodes together in terms of random walks, not only in terms of shortest paths. The shortest paths, we saw it previously in the previous investigation. The random walks is something that we are seeing here. But also more interestingly, there seems to be a shielding effect against language degradation that corresponds to an aphasic, anomic aphasia procedure. Words in the LVC have a higher probability to be correctly named by people with aphasia. This higher probability means that they are shielded against degradation coming from aphasia. So the LVC is special also in terms of linguistic processes for clinical diseases. And in another paper, we estimated the average correct pronunciation probability for words inside the LVC and for words outside of the LVC for a different spectrum of types of aphasia. And we notice consistently across types of aphasia that words in the LVC are always easier to be pronounced correctly by people with aphasia. So this is another indication that the viable cluster, the core of the mental lexicon, is shielded against language degradation this general level language degradation process that affects language processing in people with clinical impairments like aphasia. Definitely more research, more clinical research using complex networks as compasses for clinical studies is required, because this variable cluster might be key for actually modeling design strategies that facilitate language restoration and impede language degradation in people with these kinds of impairments. Okay, now very briefly, I know that my time is almost up. I still have 20 minutes, I guess, but I should give like 10 minutes for discussion, at least like 15 minutes maybe. Is it correct? Yeah, okay, I can do this. Very briefly, I would like to show how we used also multiplex networks for studying the way that we acquire words over time early on during the first phases of language acquisition in children. We do know that early word acquisition is a rather complex phenomenon. There are different theories that are currently being tested. One of them is that the environment where children live in is fundamental for determining the way that children acquire new words over time. And the way that we can model this learning environment, this is actually, there is so much freedom for doing this. We can use data and machine learning. We can use also complex networks. In this study, we used a 4-layer multiplex lexical network in order to reproduce empirical data coming from the Childis project, which mapped the way that almost 1,000 children between ages 16 and 36 months learned words over time. And what we did was the following. So we built a multiplex network considering free associations, co-occurrences in child-directed speech, feature sharing, reminiscently of Collins and Loftus' paper. So we implemented it numerically, and also phonological similarities. And we tried to reproduce the ranking of words based on the percentage of children producing a certain word over a certain month, starting from month 16 and then going through month 17 and so on, so that our ranking was indicative of the way that most children acquired words over time. So this is a normative age of acquisition. Unfortunately, we did not make predictions for individual level word prediction. We tried to reproduce this ranking based on network degrees or network features or psycholinguistic features, ranking words according to these features, like ranking first words with a higher frequency or with a higher degree and so on. Then we compared this triad ranking against the empirical one by using a goodness of prediction measurement. And in our case, this was the word gain. How many words were correctly guessed as learned at a certain age of acquisition in comparison to random guessing? And these are the results. We tested a wide number of single layer, multiplex level, and also psycholinguistic norms. And in here, I'm reporting the best ones for each category. And we noticed that very early on during language development, between months 20 and 23, multiplex closeness centrality gives the best word gains in comparison to word length, to page rank, to frequency, and also to the best single layer predictor, which was the degree in a free association network. This improved performance vanishes after month 23, so that other learning strategies give the same word gains. Before this stage, however, this is not the case. We notice that this effect is statistically robust, it's statistically important, and we need to think about this. Multiplex closeness means the possibility for words to be connected to all other words in the mental lexicon by considering jumps across layers. And this is an example here. If we consider multiplex closeness, then node C is close to all the other nodes because it is at distance 1 from all the other nodes. So all the other nodes are adjacent to it, so they are the closest possible to C. If we, however, consider only individual layers, so only the blue layer, then yeah, see, it's adjacent to A and D, but it's actually further apart from nodes B and E. And if we consider only the orange layer, the same happens. C is adjacent to B and E, but it's actually far apart from A. Only when we combine these two layers, proximity emerges. Multiplex closeness centrality exploits the jumps. If you remember when I showed the picture of the transportation system, multiplex closeness centrality makes it possible to consider at the same time semantic features, free associations, overlaps, co-occurrences, and phonological similarities all together, as it happens also in the learning environment. So in order to really account for this type of relationships, we need to consider the multiplex structure. And this is also interesting because it makes it possible to compare, okay, on one side we have multiplex closeness, which is a distance-based measure. What if we use degree? And we try, for instance, to combine the degrees in the individual layers through a certain convex combination of weights. And we play with this combination of weights and artificially make it possible to improve the word gain as much as possible. Can we produce predictions that are based on a local network feature, the degree of words across layers, that is as good as the global network feature of multiplex closeness? We try to do this in here in this plot by optimizing over the words acquired very early on, by words acquired between month 20 and 23, and by words acquired at later stages, and then generalizing these predictions across the whole time span. By combining degrees in the best possible ways in order to artificially improve as much as possible word gain, we never managed to achieve as high word gains as high as with multiplex closeness centrality. So this difference is key because it tells us that degrees are somewhat important for predicting early word acquisition, but early word acquisition is driven in an important way by distances, by global locations of words over the multiplex structure. So that if we want to improve our understanding of the way that most children learn words over time, we definitely need to account for the global structure of words in learning environments across different aspects, across a multiplex aspect of the mental lexicon. In another paper, I tried to see if this result was robust also to a change of the methodology. I used machine learning in order to predict whether a certain word was learned or not at a certain developmental stage. And I tried different basic machine learning classifiers. The best one was logistic regression. And in comparison to a simple baseline model, using only the length of a word, the frequency of a word, the number of meanings of a word, and whether a word is a verb or a noun, already this baseline model was capable of predicting word acquisition with an accuracy of roughly 62%, 63, let's say. But when I added different network features like a multiplex degree, multiplex closest centrality, multiplex page rank, or multiplex degree, or the degree of free associations, well, the improvements were different with each different network metric. The one that provided the best increases was again multiplex closest centrality. So this is again an indication that the location of words and the distances that words have from all the other ones in this multiplex structure is extremely important and fundamental in order to improve the accuracy that we can have for predicting the way that most children learn words over time. So we definitely need to do more research and also combine in a synergetic way early word acquisition with network models with artificial intelligence tools. So yes, there are strategies based on multiplex distances that have an influence over early word acquisition. And in order to wrap up, I would like to convey the idea that the mental lexicon, unfortunately, is an ideal system. We cannot directly access and play with it in the lab. What we can do, however, is access its representations and then use them for validating them with quantitative data in order to better understand how language processing works. Multiplex networks can give structure to the mental lexicon, accounting for multiple aspects of it at once. Multiplexity unveils a core in a mental lexicon that appears at a critical stage of cognitive development, around age 6 and 8, children with 6 to 8 years old. And this core is invisible to single-layer networks. Also, this core makes concepts well connected. It is important for access in people with low creativity levels, and also has a shielding effect against degradation in people with aphasia. Multiplexity and network distances can also be useful for predicting normative early word acquisition, and they can also be features for machine learning methodologies. We do need for the future more large-scale data sets, more models, and more transdisciplinary approaches, including cognitive theory, in order to really understand and predict better cognition through language processing. And I would like to thank you for your patience. And before I finish, let me do some shameful advertisement. We are doing a workshop, a satellite workshop at the next conference on complex systems. We have an amazing selection of scientific committee members who will give also potentially invited talks. We have already an invited talk by Professor Michael Vitevich, an expert on phonological networks. And we have also other participants from this workshop who are part of the scientific committee. Please have a look at the event, and if you want to, if you feel like, register at this website. So thank you again for your attention, and I'm open for discussion.
Thank you, Dr. Massimo.
Thank you.
Ольга, я тебе передаю слово.
Okay, so I can start from my questions. So my first question is, then I built multiplex networks. I can take different data sets, for example, for free associations. So like there is a Florida data set or small world network of words, and I think different others. As a result, it will be different multiplex networks, and it seems it will be the different viable clusters. Right? So did you study how this viable cluster structure depends on the data set?
Yeah, that's a very good question. Thank you. I would like to stress that the viable components that I showed, they come from different free association data sets. Like in the first one, I used the the Edinburgh Thesaurus associations. In the children one, we use the Florida norms. And in the aphasic one, we use the small word of words. And I didn't study exactly how the viable component changed, like in terms of specific words, because like these data sets have all different sizes. The Edinburgh has like 10,000 nodes, the Florida norms only 5,000, and the small word of words has like, I guess, hundreds of nodes. So my recommendation would be to go for the small word of words, which is the most recent, the largest one. But I did test whether, like, for instance, this explosive emergence of the LVC held also for the small word of words and also for the children dataset. In the children dataset, there is no viable component, which is compatible with what I found with the other paper, with the other dataset as well. And in the adults one, in the aphasic one, aphasia one, yeah, in that case, instead, yes, there is still a viable component. It's a bit larger because in that case, I'm using only free associations and phonological similarities, whereas in the creativity paper and in the scientific reports one, I use 4 layers of similarities. But in all cases, there is a sudden phase transition, and the appearance of the LVC is the same, around the same age. So this seems to point out that these patterns are robust to the different changes. And I will say also another thing, that in the scientific reports, we played with the different amount of layers that we need to have in order for the viable cluster to emerge. And it looks like as long as there is at least one phonological layer and another type of semantic layer, there will always be a phase transition that is explosive. The phonology seems to be a necessary requirement for this viable cluster to emerge all of a sudden. So this is quite interesting. So it points out to some robustness when you change data sets, but it also points to the idea that it's important when you study the viable cluster to consider at least one layer that is phonological or also orthographic. These kinds of information are important.
Okay, thank you very much.
Thank you.
So the next question.
Yeah, let's see. There are questions in the chat. Thank you. Okay, thank you.
So there is no questions from other students. So well, thank you.
No, Алена Воднева.
Передаем слово Алене. Алена.
Yeah, hi. Thank you for your presentation. I really liked the comparison with the logistic system. And maybe I missed this information, but did you take into account phonological or orthographic neighbors? Or did you mean phonological neighbors by phonologically similar words? And what did you do with homonyms?
Thank you. Thank you for this question. In these multiplex networks, homonyms are not a problem because even though they have the same phonological transcription, they now come from different physical nodes because they will have replicas that are different in the semantic layer. So
yeah, okay.
That's interesting. No, that's a big problem in phonological networks because you have these nodes that are essentially the same. And I studied them also in phonological networks. I did a few papers. They are a small but important fraction of the network. In these systems, I did not connect phonemes. I did not connect homophones with each other. I kept them as separate. And I kept them also as distinct in the semantic layer. So they are distinct nodes. About orthographic similarities, unfortunately, I didn't consider orthographic similarities in here, but I do know that Professor Su studied a multiplex network made of phonological and orthographic similarities. So maybe she will talk more about it. There is like a recent paper where she showed that considering multiplex degree was a better predictor for mistakes and confusions in processing language. So even in that case, we do need to account for both phonological similarities and orthographic similarities when considering cognitive tasks about processing language.
Okay, thank you for your answer.
Thank you. Okay.
Okay. Well, so, any questions now? I think we can stop now.
Perfect. Okay. Thank you so much. Thank you so much for inviting me.
Thank you very much for a very interesting talk.
Thank you.
Yes, your lecture was very interesting. Thank you very much.
Thank you for inviting me, for the questions.